boy. Hello. A little early today. That's good. Yeah, another day. Oh man, another day. Oh man. Hey, B. Graziano, B. Graziani 23, how are you? Okay, can you hear? We need to do a video mic check. Video check, audio check. Check, check, 1, 2. How do we sound? Check on both. Okay, lighting is on. I know that. Alright, check, check. We're good. We're good. Also, while you're here, just to double check, there's nothing on my desktop other than this. Right now, there's nothing on my desktop. I do have a couple of apps open. I just have a couple of apps open. But there's nothing on my desktop, as you can see, right? Nothing on my desktop. Okay, looks like we're good. Looks like we're pretty stable. Okay, good. Hello, everyone. It's 4:30. Yeah, 4:30 p.m. Eastern Time, February 5th. March cannot come soon enough. I'm Ming Chow, teaching professor at Tufts University. This is Introduction to Security. Yes, welcome. We are now on episode number, where's episode number 3? Yeah, this is the third episode. So, episode 1, we did packet and packet analysis. Last week we did network reconnaissance. And today we're going to talk about, well, the idea of, you don't try this at home. You're probably going to get arrested. It's called taking down the internet. The big topic that is a big problem globally, which is called distributed denial of service attack. DDoS, distributed denial of service attack. What is it? To cut the BS and to make a long story short, what a DDoS attack is, bringing down a computer, bringing down a system, just completely sending so much traffic to just pummel the system and bring it down. Yes. If you ever, do yourselves a favor, just go on, Google, do a search for DDoS, any day. I don't care what day it is. And you're going to get very recent, DDoS news. So I'm actually on page number 2. So page number 1, you have a botnet that launched a record-setting 31.4 terabits per second DDoS attack. That's a lot of data. Police shut down global DDoS operation, arresting a 20-year-old in Poland. I mean, this stuff is just, this stuff happens all the time. DDoS attacks continue to rise. DDoS is old news. The interesting thing about this week, which we're doing today's episode, is the Olympics are starting on Friday. And when a big global event happens, you sure bet there's going to be hijinks, and shenanigans, especially on the computer networks, to cause chaos. There we go. We got one. Yeah. Hijacking 10,000 devices. I mean, this is DDoS happens. A DDoS attack happens every second, every day. Been going on for years. The purpose of a distributed denial of service attack is really, to do things like cause chaos, disrupt businesses. Because even if if an online business goes down for an hour or two, that's a lot of lost revenue. DDoS attacks against school systems. During those few years, and you remember what years they were, attacks were happening against public school systems like daily. And when a computer network goes down, um, and you're teaching from home or you're learning from home, you're not going to have access to anything. Okay, so again, DDoS, not a new thing. Been around for ages. Still one of those big unsolved problems. The other thing is that about DDoS attacks is the idea is really simple. The idea is just send so much computer traffic against the target and just to bring it down. Okay, so I guess how does a DDoS attack actually work? Now you know what a DDoS attack is. You know why a DDoS attack is. Why attackers love to use DDoS attacks. Like you may be asking, like, how do you do one? Well, you're going to need a computer network, and ideally, you're going to need a lot of computers, a lot of computers on the network. Ideally, if the DDoS is for bad, you want to be using like hijacked computers or computers and devices that are infected with malware. So a computer that is infected or been hacked, infected with malware, is called a bot. A network of that is called a botnet, as here in this article. Okay, so let's take a trip back down memory lane, and let's talk about how the earliest DDoS attacks actually were done. I love this article, not this one. I mean, but it shows you 2023, 2025. I mean, now you're seeing DDoS attacks like in the terabytes and terabits like per second, not the gigabits per second. That's old news now. Cloudflare. Cloudflare is a network and security company, and they do a lot of work mitigating, and I say mitigating, distributed denial of service attacks. This article was written by the founder of Cloudflare, Matt Prince, and I absolutely love this article because it actually gives you an insight like how DDoS actually worked in the past and how you can still apply the same ideas into modern DDoS attacks to even make them more dangerous. I mean, this is old news. Gigabits per second now, old news. Okay, now we're at the terabits per second. So here's the idea of an amplification attack, a volumetric attack. We'll talk about DNS amplification in a bit. So imagine you're an attacker and you control a botnet capable of sending 100 megabits of traffic, megabits per second of traffic. That's peanut these days. Maybe knock off like a tiny website that's on a Raspberry Pi offline, but it's a small amount of traffic nowadays. Okay? So now we want to say, okay, can we do much more than that, like gigabits per second? Okay. Now let's understand like the early volumetric and amplification DDoS attacks. Anyone know who that is? Anyone know who that is? Please tell me you've seen this before. You've seen this before. You've seen this character before. Anyone a fan of cartoons? Cartoon Network? Anyone? Chime in. No one knows who this is? Damn. No one knows. Yeah, the Smurfs. Yeah, Smurf. Yes. The original, one of the most famous and earliest DDoS attack was better known as Smurf attack. Okay? So, here's the thing about ping, and we've actually talked about ping last week. Ping works very much like submarine sonar. Okay, you send an echo, and you hope you get a reply back. Okay, echo reply. And I also mentioned last week that ping or ICMP is on layer 3 of the OSI model. It's on the network layer. So there's no concept of port, no concept of handshake. Keep that in mind. Okay? Keep that in mind because that is absolutely critical for your understanding of not only the Smurf attack, but like DNS amplification. So a Smurf attack involves an attacker sending ping requests to the network broadcast address of a router configured to relay ICMP to all devices behind the router. This is a little bit confusing of wording. There's a picture on this. Okay, so here's the key. The attacker spoofs the source of the ICMP request to be the IP address of the intended victim. Okay? This is the important part. The attacker spoofs the source of the ICMP request to be the IP address of the target or the intended victim. You may be actually wondering, can you actually do that? You can spoof a source address? Yes, you can in certain cases. It says it right here. Since ICMP or ping does not include a legitimate handshake, the destination has no way of verifying if the source IP is legitimate or not. Then all those devices then respond back to the ping, thinking that the ping came from the address of the victim. Okay? So here is the picture of how Smurf actually works. So I'm an attacker, okay? I'm an attacker, and here's the victim. Okay? But you don't need to know the IP address of the attacker. What you do need to know is the IP address of the victim. The IP address of the victim is 9.9.9.9. I repeat, the IP address of the victim or the target is 9.9.9.9. Right now, the current network has 1, 2, 3, 4, 5 devices on the network. Okay, I have access to a network of 5 devices. I'm going to send a ping to each one of these devices. 1, 2, 3, 4, 5. I'm going to send a simple ping to each one of these devices, with the caveat saying that the source of the ping is from 9.9.9.9, not my actual IP address, which is the attacker's. So I'm going to send a ping to 1, 2, 3, 4, 5 devices. Each of these 5 devices, in this case is 1.1.1.2, 1.1.1.3, 1.1.1.4, 1.1.1.5, 1.1.1.6. I'm going to send a ping to each one of these devices, 2, 3, 4, 5, and 6. But the ping will have the source IP address of 9.9.9.9. So when each of these devices receive a ping, it's like, oh, okay, the sender I see is 9.9.9.9, 9.9.9.9. So then I'm just going to send a reply to, 9.9.9.9. All of a sudden, the victim here is like, received a whole bunch of ping responses. It's like from all these different IP address, and like and the victim is like, what the fuck is going on? Why am I getting all these ping replies? I didn't send anything out. Okay, this is the Smurf attack. And the big idea is because you can spoof the source IP address of things like ping. Why? Because ping doesn't have any handshake. Okay? Now, this you can really, really bring down the victim. Isn't this IP amplification? It is yes, it is. I love security. Yes, it is. Yes, it is. Yes, it is. It's amplification for sure. Now, if there are 10 devices, okay, if you have 10 devices, if I have a botnet of 10 devices here, then there will be 10 ping replies sent to the victim. If I have 100 devices, I send 100 pings, but then 100 devices will send a ping reply back to the victim. The more firepower, the more computers, the more devices that there are, sending a ping to the victim, the more firepower. More firepower, the faster you overwhelm and bring down the victim or the target. So a little brief history of time here. A little brief history of time. This was the attack that was used to take down the White House. Not the porn site, but the government website back in the late 1990s. The Smurf attack. Okay? So the key is the protocol that's being used has no handshake, that you can spoof the source IP address, um, and that's really the trick. Of course, it also goes without saying, need a ton of computers. Okay? Not just one, you need a ton of computers to do this. Now, here's the thing. Remember how last week I said that most computer systems like now turn off ping? Turn off the ability to respond to ping is because of the Smurf attack. Smurf attacks are now largely a thing of the past. Reason why is now when you buy networking equipment or when you set up like cloud services like in AWS, network operators they say, not to, you know, they basically have closed off ping. A lot of devices now close off the ability to respond to ping. In fact, if you have Mac OS, if you go to security, I think if you go to like a privacy and security, and there should be a firewall here. What the heck is it? I haven't seen this for so long. Firewall. Here we go. Network, firewall, advanced settings. Turn firewall off. No. Wait, how come it's not? How come it's not? Oh, here it is. Firewall. Firewall is here. Here you go to options. Okay, there it is. Enable stealth mode. Don't respond to or acknowledge attempts access to this computer from network test by applications such as IPM using ICMP, such as ping. So me, I have stealth mode on. So that's like default now for many systems. Does the attacker just have a bunch of extra compute? That's a great question. The attacker don't have a bunch of extra computers. They use hacked computers from around the world. Wait a minute. Whoa, 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 whoa. How the hell you do that? How you hack? How do you have a network of like hacked computers? Infect them with malware? Or okay, hold on. Let me answer academic student 47 question. That's a really good one. Usually it's done by way of a botnet. Botnets are responsible for the largest DDoS on like how they. Okay, here it is. This is a good resource for you. This is for academic student 47. This is a really good question for academic student 47. Usually hacked computers on a network, like coffee makers, refrigerators. A botnet refers to a group of computers that have been infected with malware or have been hacked of some way, shape, or form. Okay? Self-propagating botnet to recruit additional botnet through different channels, yada yada yada. Mirai was based off a whole bunch of hacked webcams. Reason for botnet ranges from hacktivism to state-sponsored. So once you actually hack a computer, like a device, or infect it with malware, you have a network. And here's how a botnet is controlled. There usually is some command and control software that's installed. So I hope this answers your questions. Academic student 47 is a really good one. Okay, so a whole bunch of hacked computers, bot masters in the middle. There's for each and every one of these infected computers. There's also some command and control software that's installed on each and every one of these bots. Furthermore, remember here's another way, which a lot of people try. Like you may be wondering, like how do I actually attack a whole bunch of machines? Remember last week we talked about Shodan? Now, there's like a lot of vulnerable machines. You probably have seen in lab number 3, there's a lot of vulnerable stuff out there that are just exposed on Shodan. So you can use that information to actually see, you get the idea. So, academic student, Shodan is also an avenue as well. There's a reason why not only defenders but also attackers love to use Shodan because it exposes so much stuff out there on the internet. And you can get and once you get the IP and all the information about those devices, there may be avenues to get in. B. Graziano, could you use a VM? You could, but here's the problem with virtual machines. You need a lot of them. Lots of virtual machine. Because one running just like two virtual machine, it's resource intensive. So you could, but it's just not enough. You could use machine for like a lab environment, but to actually use VMs to really launch a distributed analysis service attack, for real, it's not enough. It's not enough. Okay? So, alright. So, Smurf is largely a thing of the past because, a lot of devices now turn off ping. But remember the trick of why the Smurf attack worked. It took advantage of ICMP or ping. Ping does not include a handshake. Therefore, destination has no way of verifying if the source IP is legitimate. Now, can anyone tell me what doesn't use a handshake? Give me a protocol or something that does not use a handshake. In other words, no TCP. Can anyone think of a protocol off the top of their head that does not use a handshake, that does not use TCP? Okay, UDP. UDP. What is UDP? UDP is a user datagram protocol. It is used for things like streaming video. UDP is fast. UDP, okay, used for video playback, okay. There's no handshake at all. Okay, TCP versus UDP. Here it is. This is a good illustration. I'll make a copy of this, but hang on, you get the idea. You get the idea. UDP is faster but less reliable than TCP, another transport protocol. Now, everything that you learned so far, TCP three-way handshake, sing sing ack and ack. Okay, TCP starts with a handshake. UDP is just, I'm just gonna fire a whole bunch of stuff at you. Catch it if you can. If you drop it, too bad. That's fine. UDP does not go through the process. One computer can just begin sending data to another. Okay? So yeah, UDP. No handshake at all. But does anyone know a fun application that uses UDP? Actually, the answer was right here. Video playback or DNS lookups. Domain name systems. Is it domain name systems? Yeah, domain name system. Well, sometimes I say domain name server. Think of domain name system as it's a lookup table. It's to translate domain names into the IP address, like a phone book. Okay? Now I have a fun question for each and every one of you here. You know how to do a DNS lookup on the terminal? This is important. Anyone how to do a DNS lookup? So DNS, generally speaking, uses UDP. Okay. Oh, okay. So we have a contest here. We have Lasagna and Mastermind Golem. We have Dig and we have NS Lookup. You're both right. You're both right. However, one is preferred over another. In this case, Dig is going to be preferred over another. Why? Because Dig is 3 characters long. NS Lookup has, I'm trying to count off the 1, 2, 3. Well, how many characters are there for NS Lookup? 1, 2, 3, 4, 5, 6, 7, 8, 9? 8 characters? Yeah, 8 characters for NSLOOKUP. Dig and NSLOOKUP are both used for DNS. But we're going to use dig because dig is 3 characters long and not 8. Size matters in this case. Okay, give me your favorite domain. Your favorite website. You don't put the .com because I think you get blocked on the Twitch chat. So I'm going to use dig. Give me your favorite website. Someone. I don't care. Give me a website. Don't say the dot. Don't give the dot part out. I said no dot part. So Matt, you got censored because you put probably like .com. Ooh, okay. Neocities.org. Okay. Neocities.org. Okay. How many characters are there? How many characters? Count the number of characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 characters? Your input is 17 characters. Got that? 17, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 7. Yeah, 17 characters. Your input size is 17. What's your output size going to be, though? How many characters are here? So you have an input of 17. Do a character count. So your input of 17 results in 470 characters. 417 characters divided by 17, that's a 27.6 time, that's a pretty good payout. That's a really good payout. So if I go to dig, if I go to my favorite site right now, Reddit, okay, actually, you know what, to make something even crazy, digx.com, 1, 2, 3, 4, 5, 6, 7, 8, 9 characters, and you get all this mess. You have a 9 character input, that's pretty low. 9 characters, 452. And that's a 50 times amplification. That's a 50 time. So that's a pretty good payout. 9 characters, input 452 characters of all this, and you send that all back to a target or a victim, kablooey. And that's the whole idea of a DNS amplification. So DNS amplification is there are 2 attack vectors. The query number 1 is that the query can be set with a spoof source address by way of a protocol like ICMP or UDP that does not require a handshake. And 2, the response to the query is significantly larger than the query itself. That's how DNS works. You ask a question, you get an answer back. The response to the query is significantly larger than the query itself. Like, for example, dig x.com is only 9 characters long, you have 450 something characters. DNS is used every day. It's used every second. DNS uses UDP. DNS queries are typically transmitted over UDP, meaning like ICMP, like ping request, in a Smurf attack, they can fire and forget. As a result, their source can be spoofed and the receiver have no way of determining its veracity before responding. DNS is also capable of generating a much larger response in a query. For example, you can send the following tiny query of an open X is the IP address of an open DNS resolver, and you get back and there are a ton of these on the internet, shit ton, and you get back a gigantic response. That's a lot of data. That's a 64 byte query input that resulted in a 3,223 byte response. In other words, an attacker is able to achieve a 50-time amplification over whatever traffic that they can initiate to an open DNS resolver. And you know what? Stuff like this still happens today. And this is the idea of an amplification, an amplification DDoS attack, which are really actually common these days. So now you may be wondering a couple of questions. Now you know what a DDoS attack is, why they happen, how you do it, in theory, but can we do one in practice? Can you do one using a programming language? Can you do one at home? Also, how do you actually spoof a source IP address of a packet? Can you do all that? We'll answer both questions. That's what we're going to do now. And yes, we will show you how to do a DNS amplification DDoS attack using Python. And that's what we're going to use. We're going to use Python, and we're going to use a library called Scapy. Yeah, Scapy. Scapy or Scappy. I call it Scapy. I got beat up this summer and to call it Scapy. Go to scapy.net. Scapy or Scappy is a Python library to do packet manipulation. So Scapy. The documentation is a little bit wonky. So you can use Scapy to forge or decode packets in a wide number of protocols over the wire, capture them. So you can use Scapy to read and write packets. Not bad. It's also cross-platform. Okay, but there's a problem. Scapy can be a bit slow. It's written in Python. It's for Python. So you're not going to get like native C performance. Okay. And that's a little tutorial right here. Okay, so I'm on a Mac OS right now. I'm on a Mac OS. My desktop is empty. I'm going to make the alarm. I'll make a directory called alarm. Alright, I'm going to cd into alarm. Now, what's very important is that you have the latest version of Python. You need Python 3 to use Scapy. So I use Homebrew. So I do brew install Python 3. I already installed it already. You absolutely need Python 3. Not 2. This isn't going to work. 2 has been deprecated. The next thing I want to do is, the next thing you need to do is, because you're using the latest version of Python, you just can't run and install program, Python libraries on the fly anymore. You have to do something called virtual environment. Python, a virtual environment is this. It's a tool to create isolated Python environments. Back in the days, if you install Python libraries, it would be installed. You can install them system-wide. But then you have version dependency issues, permission issues, and a whole host of other problems. Now the whole idea of having a virtual environment is, think of it as giving an application like a sandbox. Okay? It's like a sandbox that you can play with. Okay? Have its own installation directory that don't share library with other virtual environments. Okay? So how you actually enable, right now this folder is empty if I do an ls-la. So to enable a virtual environment in this folder, you have to do something called Python 3 minus module venv for virtual env, and I'm going to call my folder called env. So now, as you can see, I have a folder called env. If I do an ls-env, you can see the binary. I can see Python. If I do an ls-l, you can see symbolic links and aliases. Now the next step I need to do is I need to activate my virtual environment, which is I'm going to do source env pin activate. And now you notice preceding my host, my computer name, you see in parentheses env. That means the virtual environment is activated. Now I have a virtual environment enabled. Now I can install Python packages that I want for this app or for this folder I'm working in. So I would do something called pip install Scapy. And there it is. Installed just fine. And this is platform independent. Next thing I do now, there are two modes of Scapy. There is command line mode and also library mode. That means you write a Python program. Okay? Actually, Begraziani pip is goated, but now the real goat is UV. Just a heads up. UV is now the goat. Look into it. It's great. So now I'm just going to type Scapy. And this is what is called command line mode. So I can actually, using command line mode, I can create packets, simple stuff on the fly. Okay? So here is how I can send a packet, a ping packet, and send it out. So I have Wireshark open. I am going to capture on EN6. Hey, that's a Twitch stream. Our Twitch stream looks like it's all TCP. Nice. So I'm going to filter by IP ADDR equals 192.168.1.18. So I'm going to do something called packet. Packet. You know what? Can I clear the screen? No, I have to. Yeah, this one I'm going to do. There you go. So everyone can see. So I'm going to do packet equals the IP. Now, this is the IP layer of a packet. This is where you can set the source and the destination address. I'm going to do destination address 192.168.1.18. And now the next thing I will do is I will do a layer. The slash also means, okay, add another part of for the packet. I'm just going to call it ICMP. So I'm going to create a ping packet, an ICMP packet, to the destination 192.168.1.18. Watch what happens. Hit the enter key. Nothing happened. Right. Nothing here yet. I didn't send it out. I just created a packet. Now, if I do packet.show, and you can see the details of the packet. IPv4, no flags, no protocol, checksum, source, destination, 192.168, the code, so you can see the source is 192.168.1.219, 192.168.1.18 is the destination. It's an ICMP packet, and these are all the ICMP or ping headers. Packet.show gives you like a pull drill down showing all the layers of a packet. Now to send the packet, we're going to do send packet. Watch what happens. Watch my Wireshark. Bing! There it is. You can see the ping packet being sent, the request made, and the reply made. Not bad. Not bad. Not bad. Do it again. You can hit the up arrow. Bing! Another one. Okay? Another one. Not bad. Okay now. So how do you forge a source IP address? That's easy. How you forge a source IP address? Oh, damn. So you do something like, I'm going to overwrite the packet. Packet equals IP src. I'm going to give it a source IP address of 1.1.1.1. Oh. DST equals 192.168.1.18 ICMP. packet.show. Look at source IP address is 1.1.1.1. It can be any IP address that you want. Destination is 192.168.1.18. It's a ping packet. You can't, if it's a TCP packet, nah, this is not gonna, forging a source IP address is not gonna fly. Now watch what happens when I send the packet out. It gets really interesting. Ready? Interesting. The source is 1.1.1.1, but the destination is 192.168.1.18. Notice a request got sent out. There's no reply. Because the reply is 192.168.1.18 is sending to 1.1.1.1. So this makes total sense. The request is sent from my machine, of course. Like if you actually just drill down on the details, you can see source address. Yeah, there it is. Source address is 192.168.1.1.1. Destination is 192.168.1.18. Everything that I just sent. But there's no reply sent because only the machine at Cloudflare at 1.1.1.1 will see the ping. We'll see the we'll see the reply. Okay. So yeah, I mean, for protocols like to just forge or to spoof a source IP address, when you're creating a packet, all you just need to do is to set the SRC to be whatever you want. DST, of course, that's pretty standard. That's all you have to do. You can only spoof the source IP address for non-TCP, non-handshake protocol, ping UDP. So now you may be wondering, wait, using this technique, can we actually run a DNS amplification using Scapy? I'm going to leave that to my friend John Hammond. He'll show you. For now, I'm going to quit out of Scapy command line mode. I don't need this anymore. However, it doesn't mean we're done. I'm going to quit Wireshark. Don't need this anymore. Stop and quit. And I want to introduce you to the fourth lab of this course. The fourth lab of this course is to build an incident alarm. It's an incident alarm. Remember in lab number 2, you played with Wireshark. Lab number 2, just a review. It's all publicly available. Packet sleuth. You're just using Wireshark to analyze, to rip out sensitive information, username, passwords, and stuff. You know what I'm going to do? I'm going to download set1.pcap into the alarm folder. I'm also going to download set2. So now my alarm folder got both set1 and set2.pcap, and you'll see why I did that. I'm not going to download the 61. That's a pain in the ass. So now you're going to write a program in Python and Scapy that just detects username and passwords. You're going to actually use this alarm to detect bin, null, Christmas tree scans. You're going to actually use and build an alarm that someone is scanning SMB, RDP, and VNC. And I give you the packets, the PCAPs for NICTO, SMB, RDP, and VNC. Right? They're here. Yeah, all here. And you're going to write one simple Python program that does this, does all of these, to detect all of these items. In fact, even a better deal. I already did the hard work for you. I give you a starter code. Right here, it's an alarm.py. Can I download this? Saved? Here it is. Does this shit work? Maybe not. Copy. Maybe I should get Visual Studio Code back. It's called alarm.py. All right, here we go. I already did the hard work for you. The only thing that you need to do for lab number 4, for this lab, the only thing that you need to do, I give you the instructions and everything, is to modify the packet callback function. That's it. This is the only thing that you do. The only thing that you do is to modify the packet callback function. Don't write any extra function. Don't make it pretty. Don't worry about like code modularity. You don't want to do that, especially when time and performance is important. Now, I saved this to my alarm folder. You see I have PCAP files here. Watch this. I'm still using the virtual environment, but if I do Python 3 alarm.py, it should work with no errors. Shit, sorry. Sniffing by default is going to run as a sniffer. You need to be root. This program also has sniffer mode as well to enable, but you're not going to be caring so much about sniffer mode unless you really want to. What is important is you go to the help menu. Okay, there is sniffer mode, which is -I, and there is -R to read in a PCAP file. So let's do Python 3 alarm.py -R set1.pcap. And run, and it just analyze. So each and every packet in set1.pcap goes, each packet goes into packet callback. But let's take a look at how packet callback works right now. There's exception handling that if packet sub tcp.dport equals 80, then print HTTP web traffic is detected. Okay, well, if you remember from set1.pcap in lab number 2, it was not web related. Set2 was. So if I actually feed in set2.pcap into the alarm, okay, now we actually have the web traffic exposed. We can modify this program right now. You can do elif packet sub tcp dot dport equals 21. Print. Maybe I should go back to Visual Studio Code every so often. Print FTP. Does this work now for set 1? Yep, that works. Okay, that works. Now, how about this? I can also just screw this whole thing. There is also something called if packet dot has, I think it's has layer. I think that's the routine. Has layer TCP, then print packet dot show. I think this is the way to go. I could be wrong. Yeah, it does. That works. So if packet dot has layer, the other way of using the bracket notation also works, but it's has layer all one word. If packet dot has layer TCP, then packet dot show, and I'm running alarm now on set1.pcap, I can do a pipe more, and now you can see each and every packet. You can see the source port, destination port. You can see the flags. TCP has source port, destination port, sequence number, acknowledgement, flags. If you want to print out the flags, comment this out. Print packet sub TCP dot is it flags? Flags. Yep. Watch this. Do this again. Now you can see, look at the first 3 packets. Sing, sing, cack, and ack. If you want to get the data, oh man. If you want to get the actual data, I think it is packet sub raw. I think this is it. Oh man, this is where I have to use like Scappy print TCP raw. I always forget. Oh, it's a print TCP payload. What the heck? Ah, here it is. Yeah, let me see if this one works. No, it's the... This may do it. I think this may work. I think you have to do called decode to ASCII. I think this may work. Nope. What is it? I keep forgetting what it is. I'll put it in a cheat sheet for you. How do you print out the payload? .pay, yeah. Yeah, I mean, I have a cheat sheet of these things. I'll send it to you as a... Oh, what is it? So how you get like the piece of the email or the text. I think it is something like, does anyone know how to do it? I forget. Extracting TCP, I already saw that. TCP output dot, oh, I don't think that's it. No, but yeah, there is a way to get like the username to get the plain text data out. It's not raw. I forget what it is. I always forget what it is. I'll send it in a cheat sheet. But yeah, if I go back, comment this out, and do a packet.show. Hold on. Oh, it's load. There you go. That'll work back. I think this one works. The raw layer load. Please work. Nope. Print packets. So is it raw? Oh yeah, it has to be. Okay, yeah. There you go. Bing. There you go. You do need to like decode this into ASCII. Okay, so we actually use our brain. Yeah, these are all okay. There it is, the username. It should look very familiar. Should look very familiar. All right. That's the binary data. Yeah. Can I do grep JPEG? Yep. There you go. I'll let you deal with it though. You can have some fun with this. So now, as I promised, now you have an introduction to lab number 4. Now you have an introduction to lab number 4. You have also an introduction to Scapy. So you may be wondering, how do you do a DNS amplification? So I'm going to turn it over to a friend. He did this for us many years ago, did this tutorial, John Hammond. So John Hammond, security, he's a cybersecurity researcher. He has a very popular YouTube channel as well. He's a friend of ours. I think he's at Huntress Labs the last time I checked. He does read 2.11 million subscribers. Wow, he makes me look like a plebe. I need a job or something. But yeah, he's a principal security researcher at Huntress. And he did this tutorial for us during DEF CON in I think it was 2020 or 2021. But I am going to turn it over to John. And I'm going to do transition.
Alrighty, hello everyone. Welcome. Thank you for tuning in. I appreciate you being here. This is a talk and presentation titled Take Down the Internet with Scapy. I'm presenting this as part of DEF CON 28 or DEF CON Safe Mode, and I'm here at the Packet Hacking Village. So let's dive into the presentation, but before we do, I've got to say this. I've said it before, I'm about to say it now, and I'm certainly going to say it again many, many times throughout the presentation. Thank you. Thank you for being here.
I'm going to fast forward. Hold on.
Could be interactive, and you could work inside of an interpreter with a manual, like typing in commands and getting that returned back to you, like interactive shell. Or you could work with it inside of a script and have Python just import Scapy as a whole module. And you can access all of the code, the functions, the variables, all of that functionality that Scapy offers inside of your Python scripts, inside of Python. Now, this is crazy cool because we can work with TCP packets, UDP packets, any other network stuff, maybe CAN bus protocols or Bluetooth. There's so much more, and we could dive into some of the documentation for Scapy. I always want to point people to the real documentation because that's where the real stuff is, right? I'm not going to be the expert, sorry. I don't think you would call yourself the expert, and I'm not saying that to be mean. I'm just trying to say the source code is the truth, right? The documentation is the real accurate stuff. That's what's really there, really built in, and the official source is what's good to go to when you need help or you're trying to learn something new. Obviously, there's a man page for the command if you wanted to fire that up. Obviously, they've got an online web presence. You can check them out at scapy.net. And they have official documentation over at readthedocs.io. And of course, a GitHub page. So you can go take a look at the source code. It's open source. It's awesome. It's all Python, good stuff. The website is actually fantastic. They have a page over there called Awesome Scapy. And that will showcase other tools, exploits, and some sample code to use. And it's really, really cool. They have some good stuff on Wi-Fi, like mapping and tracking Wi-Fi networks through 802.11, making a roaming access point, performing some man-in-the-middle attacks, some Tor, onion router protocol stuff, tons and tons of great stuff. Even CVEs and exploits for common attacks, or stuff from Crack, the attack against WPA2. Super duper cool. Really recommend you go check that out. Okay, now let's talk about the basic syntax of Scapy, because if we want to use it, we have to know how to. I say that Scapy is Pythonic in that the syntax that it uses when you're working with the module, you're working with Python objects, right? The same way most everything in Python really is that you're interacting and working with an object that has methods and properties and all these attributes and things you could work with that are really under the hood, right? Functions and variables, just with a kind of a different decorated name. But being object-oriented means we can do some kind of nifty things with it. Maybe not all the time. I'm not trying to say OOP is the way, but it's nice to have that kind of built into the language when necessary. So you can see I'm working in like a little bit of a script here, right? I've got a shebang line set up. I'm going to work with Python 3 as my interpreter. And I'm going to use that from scapy.all import everything, or the asterisk, the star, the wildcard, to pull in everything that Scapy module has into my current namespace. So I can interact with it and I can work with it through Python.
You know what? Let's see if I can go to the get working overtime part. Ooh, here it is.
minuscule example of one thing that Scapy could do. What we could do with that packet, or with many other packets, is put that together into a PCAP file, write it out to a packet capture archive. Or we could read in a packet capture archive or a PCAP file, read through it, loop through it, do interesting things with it. Or we could sniff and listen and actually capture live packets and dissect them or forge new ones, etc. With filters, import and exports, create graphs, reports, tables, etc., etc. And obviously, all of those specific different protocols that we would want to work with, we can. And then maybe we could turn it into more of the offensive side. We could probe or scan or attack networks, fuzz specific aspects of a protocol, or send malformed packets. And we could do crazy tricks like, ARP poisoning, or do some specific kinds of scans, etc., etc. The benefit behind all of this, and this is what makes it so awesome, is that it can all be automated and you can write it and you have that fine-tuned control all within Python. You have the entire arsenal of the Python language and libraries, modules, other tools that you can use and pull into it. So that's super duper cool. Now let's get into the good stuff. Let's get into the really cool attacks that could potentially take down the internet, right? So we'll start small, we'll start with some simple things, and then we'll slowly kind of zoom in onto more complex stuff. But just to kind of whet your appetite, let's start with the ping of death. Interesting name, right? So the ping of death attack is a denial of service attack where the attacker will stop a machine by sending a large ping packet. So large, in fact, that the machine can't handle it. It'll choke. There's so much data in that packet that the machine doesn't know what to do with it, and it'll freeze up or just fall over or crash. We talked about ping packets in the previous example, or that script and source code that I showed you earlier, when we were looking at that ICMP protocol, or the Internet Control Message Protocol. So typically, ping packets are very small, but IPv4 ping packets can be much larger, up to the maximum allowable packet size of 65,535 bytes. Some systems might not be designed to actually handle packets larger than this maximum, and they might be vulnerable to packets at that size, and they're sensitive to it, they'll choke, and they'll fall over. When this large evil packet is sent from the attacker to the victim, the packet becomes fragmented into different segments, each of which will be smaller than the maximum size limit. When the target and victim actually attempts to put these pieces all back together, eventually that total size will exceed that maximum size limit, and maybe a buffer overflow occurs or something goes wrong and that machine can't handle it. It'll freeze, it'll choke, it'll crash. So we're using this example where the ICMP echo or that ping packet could be used for this attack, but really anything that sends an IP datagram that can hold more data or can have this attached information that extends beyond that maximum size could be used for this attack. That could be TCP or UDP or any IPX stuff. Admittedly, the ping of death attack is kind of old and a little outdated, but I think it works as a really cool and simple, quick jumping off point or starting point for us to take a look at some of these evil, nefarious things that we could do with Python and Scapy. So with that said, let's take a look at the source code here. You can see I'm using the send function, which is part of Scapy. We say we've imported everything into our namespace. You could also send just one packet and receive the information back, or send packets inside of a loop. But for just one quick shot, firing the gun, we can use this send function here. We'll create a fragment, as kind of we discussed earlier. Sending fragments that might be rebuilt and reassembled by the victim machine that could potentially cause it to crash and choke. And inside of that, we'll build this ICMP packet just as we've done before in that previous example. However, you can see there at the end, we use another divider or to add in another layer or some more information into this packet. And I just use a simple dummy string. I just use the letter X and I multiply it by this large number. So I have this data payload, this information that I've strapped to this ping packet so that I can send a ping of death that's just a little too big. And maybe that machine is biting off more than it can chew, it'll choke and it'll fall right over. I did mention, though, that this ping of death attack is less common today, right? More so now, you'll see other kinds of attacks that are still this denial of service attack, right? We're being a jerk. We're overwhelming, flooding, and just bogging down the resources on that victim or target. So one of the more common ones you'll see now is perhaps an ICMP or a ping flood. And we can certainly send other kinds of floods. One of the most common ones you might see is a SYN flood. SYN flood is another denial of service or DDoS attack, which will make that server, your victim, unavailable to respond. It'll be just too busy. It'll be bogged down. It'll be hosed because something will be consuming all of the available server resources. We're going to cause that by sending packets with that SYN flag set. So you know TCP packets, right? TCP being the transmission control protocol, which ensures there is a connection in place by using the three-way handshake, right? The client on one side of the conversation will send to the server a packet with the SYN flag set to synchronize or start the conversation and begin requesting communication. The server over on the other end of the conversation will say and respond back with a SYN ACK packet or a packet sent with those flags set. Finally, the client, knowing that the server has responded, that someone actually answered the phone, it will respond once more with an ACK flag set on a packet, or the acknowledgement, okay, someone is listening and we can talk, we can have this conversation. Interesting thing though, on step 2 of that process, or in the middle of the three-way handshake communication, the server, while it sends that SYN ACK packet, it will wait to receive that ACK packet from the client so that it can begin having this conversation. So the attack is simple. We just send a ton of SYN packets where we're just starting all these conversations. We're dialing the phone, but once someone answers, we don't care. We don't respond to them with an ACK packet. So they're overwhelmed, right? The phone keeps ringing. They're going to pick it up and they're going to want to talk to someone, but no one will be there. They're just not having this conversation, but they're still holding the phone and more are ringing. That will hog all the resources. That will cause that target victim to not be able to respond to other legitimate traffic because, okay, hey, they're busy, tied up with other stuff. All those resources are being utilized right now. Because this attack brings that server to the halfway point in the three-way handshake, right? They've started the communication but have not responded to the server's acknowledgement. That means that it's halfway communicated. That's why it's called that half-open attack. Kind of interesting. So let's take a look at the source code, right? Scapy, again, makes this super duper easy. We're performing this attack in, realistically, 2 lines of code that could even be shortened to 1 because, hey, maybe we could abstract out that object that's not necessary for that SYN flood. We could just pass that to the function. So I'm creating the SYN flood object or variable, right? I send in a keyword argument for the destination. Again, just an IP address we'll use. We'll set an ID number for that packet and we'll specify the time to live. These values aren't extremely important for kind of just our discussion, but obviously that next layer certainly is. We create a TCP portion of this packet, and that sport, or S port is how you should read that, for our source port, that's just going to be a random ephemeral port that Scapy will help us generate with that rand short function there. That'll return something that make it look like, okay, we're coming from a different port every time. The D port, or the destination port, will be passed in as a list or a little Python array. We'll just send this over to port 80 HTTP. You could specify this to whatever you wanted to, maybe SSH or anything specifically. Specify a sequence number, specify an acknowledgement number. Again, for this example, those don't really matter all that much, but maybe they could in other scenarios. The window size, and the most important thing here, the flags that are set on this TCP packet. Obviously, I'm just passing in a string here with that capital S, And certainly enough, that stands for SYN, right? The SYN flag has been set on this packet. So we have created one packet that is just a SYN packet. The very, very first step in that TCP three-way handshake. The next line below, we're going to end up using that SR loop function that Scapy makes available to us. And that is going to send and receive packets in a loop. So we will repeatedly, over and over and over again, send this packet. The keyword arguments there, that inter or the interval, we'll send those at 0.3 of a second. We'll retry every 2 seconds if that kind of gets dropped. And we'll have a timeout of 4 seconds. Again, those are a little extraneous, but the point that we're getting across right now is that we are looping a SYN packet being sent over and over and over again. We are flooding that target victim server with this SYN flood attack. In the case of the line of code there, we have an answered and unanswered information that's being stored as a return value of that SR loop. That'll just return a tuple, okay, or a list of what packets actually had a response and what didn't. The point that I'm trying to get across is that just these 2 lines of code are putting together this attack. And it's super duper simple. All you've done is outlined the structure. You've orchestrated this packet, and now you can put it to work. You can weaponize it as a SYN flood. You might notice, though, in this example, with this setup right here, we're sending this SYN flood attack just with our attacker machine. One machine. So potentially, that endpoint or that target, the victim server, once it realizes, hey, I'm under attack, right? I'm in danger. If they kind of had the opportunity to look through some logs or could figure something out and determine, oh, I know the source of this attack, I can just block it off. Well, you're totally right. That's absolutely doable. For that reason, this kind of thing isn't often done just with one host, just with one attacking machine. So you bring into the conversation, okay, we're performing a denial of service attack, a DOS attack or a DOS attack. But if we had more machines in this pool, if we were attacking with multiple hosts, we could be performing a distributed denial of service attack, or that DDoS, DDoS. That might make it a little bit harder to do, harder to track down, harder to trace. However, we could do even more. We could go one step beyond that when we say our source IP address, we don't want that to look like it's coming from us. We want to hide it. We want to mask it and obfuscate that just a little bit more. But you can tell with Scapy, we are crafting our packets at the granular level. What's to stop us from specifying just that information, just the bytes, the real information that we need within that header of the packet? We could say that our source IP address comes from a different IP address, comes from a different host. We can spoof our IP address simply by passing in the keyword argument. Just as you see the example there, we specify that DST keyword argument as an IP address string. We could just as easily specify SRC, or the source IP address, and make it look like we are coming from a different location. We can spoof our IP address super easily with Scapy. And we can use that as a segue into the next attack, DNS amplification attacks. A DNS amplification attack is a really interesting technique that abuses the regular functionality of DNS, or the domain name system, to again overwhelm, spam, and flood a target or victim machine. The way that this works is that the attacker actually sends a legitimate regular request to a DNS name server asking for as much information as they can. So their request is a regular kind of small, tiny packet just asking for information, and the domain name server will respond with as much information as possible, and that way you get a much larger packet in response. The trick here is that with this DNS amplification attack, the attacker sets their IP address, the source, back to the actual victim or the target server that they're aiming to overwhelm and choke. You can see this here in the source code, right? We're defining, again, another object or variable to keep track of our packet. We're defining an IP header, but interestingly enough, we supply that SRC keyword value, or the source IP address of the packet that we're going to be formulating. Note, this will act as our victim. This is the target machine that will have the domain name server send back that large request. You can see again our division symbol or the / to add new layers, and we're adding a UDP packet portion, right? We'll set the D port or the destination port to 53, the default port for the domain name system or DNS servers. And what we're going to query from this DNS is anything we'd particularly like. Here, I'll just ask for anything regarding google.com or that domain. You could, of course, ask for any type or any resource record you'd like, an A record, a text record, a CNAME record. Generally, with this attack, you could expect to see the attacker request for any, as in return all of the resource records you could give me. We'll have that packet formulated, stored, and encapsulated in that DNS AMP object and variable, and again, we will just send that packet along. The DNS server will respond accordingly. It will give all the information it can, but send it to that source IP address, not our actual attacker. That will flood and overwhelm, choke that target victim server. Obviously, you'd want to have more than one attack or one attacking machine doing this. You could perform this distributed denial of service, right? That DDoS, or send this request multiple times. But I think this attack is really cool and really interesting, right? If you put it in kind of layman's term or a normal human explanation, say you are at the drive-thru ordering some fast food to go or whatever the case may be. Let's say you ask the person or the teller that's chatting with you and taking your order, I want one burger or I want one drink or whatever. Typically, that job of the teller will read back your order, right? So envision this scenario. You as the driver, right? You as the attacker, you say, I want everything on the menu. And then before they can read your order back to you, you drive away and let that next person go ahead and actually hear all that information. So while you just asked for a small tiny thing and a simple, hey, give me everything you've got, the next person or your target or your victim is going to be read and enumerated and receive all of the information. So maybe, I don't know, what a 1 scale for your packet could respond to a 10 in the response and what that teller will read out to that other person or that individual. Kind of cool. And obviously, another added benefit to this is that the attacker is performing this attack indirectly. They make this request out to an open and accessible DNS resolver, and it will respond and just send that information out to the actual target or victim themselves. The attacker doesn't really leave any fingerprints or a trace on the target. It's not reaching it directly. It is an indirect attack. You can see that here again with that syntax, but as always, Scapy is making this really, really simple and honestly really easy. Okay, now let's talk about our finale attack. I want to discuss BGP abuse.
Have a good one, folks.
So BGP is the Border Gateway Protocol, and that is the